And let me share my screen with you all. So as we plan for the semester, I know that we had to do certain adjustment throughout the semester. Now we are into the week 14, where we're going to cover chapter 8, and not only that, at the end of this week, you have your exam 3 coming up. I'm sure you are already aware of it. That is Monday coming week. I have posted exam 3 study guide right here. If you click the assignment exam 3, you will see what areas you need to look after. Basically from chapter 5 and 6, everything we discussed. To better prepare with your exam 3, my advice would be your homework assignment 5 and 6. Get those two completed. I know the 5 was due last week. I was not able to grade it yet. Hopefully within this week. And your 6 is up and ready. That is also due on the same day. Completing assignment 6, that is from chapter 6, is gonna be very helpful to you to better answer your exam 3. Okay, so exam 3 will be available for everyone throughout the day, Monday, starting 000 a.m. Early in the morning until the midnight. You have 24 hours to answer the 24 hours, 1 minute less than the 24 hours less than to answer the questions. So you can keep the answers saved and submit before the end of the day. Okay, that is exam 3 requirement. As I said again, exam 3 is all from chapter 5 and 6. Other than that, any other announcement? Okay, your final exam, also the study guide also posted. Basically, it's going to cover almost everything, but heavily weighted towards chapter 10, 11, and I would say rather 5 and 6, which you are going to take this week. 5 and 6, and 10 and 11. Then yeah, that's all about the announcements. And again, even though we do not do 3 live meetings, feel free to contact me. I have seen at least a few students who used to keep it as a habit or contact me with the questions about homework assignment and chapter concept clarification whenever they need help. So anyone else who need the same help, feel free to contact me. You don't need to stick to just Monday, Wednesday, Friday. Even if you need help on Tuesdays and Thursdays, you may reach out to me. Okay, with saying that, let me jump into chapter 8, where we're going to discuss about the process management. So in the previous chapters, up to chapter 6, our discussion was mainly on how the PEP9 architecture, von Neumann architecture based PEP9 implementation of a processor, how it's going to handle process. How it's going to handle process. So basically, a process is a program at the time of the execution. We call it a process. So you use a processor to execute a process. So almost every example that we have discussed so far, each processor use only one process at a time. So we send one process at a time to a processor. So we are not overly worried because only one is being sent to the processor. The processor will deal with it as far as it is able, because the entire memory is dedicated for that particular process, right? No much of a big deal, because no one else is trying to use the same memory allocation. So entire memory is always available to the processor. So now the issue is, what's going to happen when you have more than one process looking for a processor, right? So the textbook start with the discussion with the single user, multi-user, and the real-time process. So operating systems that we use, single user operating systems are mainly the operating system that goes with the mobile devices. Most of the mobile devices can make one application running, can run a one application at a time. You probably have seen this in the most of the mobile devices. I'm sure some of the modern mobile devices are able to run some background applications, even though those are not visible in your screen, right? For an example, the old day, before any application that probably you have seen before 2015 or so, most of the mobile devices can't even split its screen, right? Only one application can be running the entire screen. So, but now the modern day mobile devices may let you to split your screen and run two applications at a time. So by the architecture, mobile devices has built in a way that one user or the single user application. So basically single process, single large scale process running on the top. But still there are some processes in the behind the screen, mainly the system programs, system programs, operating system process running in the background, right? So the multi-user will be the what your desktop or your laptop is. There are plenty of applications running with parallel to one another. So the easy example that I can take would be, assume you have a word processing application running. At the same time, you have some media player that playing some music in the background. So media player music is being playing in the background, and your word processing application, which you are working, which you are writing. So while you are writing, the priority is being given to the word processing, because every character that you write is need to be processed. If you remember it right, in the PEP9 architecture, every character you enter is a deco input, right? Decimal input, or it has been sent to the program and kept it saved. So there need to be certain process behind the screen to make it work. And at the same time, in the media player that we were thought of running at the same time, so media player will take about a few seconds or maybe even more than that into a cache and continue its running. So if your computer only has a one or single processor computer, so those have to be switched between one another every time when you hit a keyboard stroke. It needs to be processed. If your CPU is not able to load at least a few seconds to its memory, when you hit the keyboard, the program, the background program that play the media or the audio track need to be stopped for a while, right? But fortunately, the processor is built in a way that it can keep a cache memory for a certain time. So even though it is not used that processor in a given time at the time that you hit the keyboard, still it is continue the audio track in the background, right? But if you have a multi-cores, right, dual core or multi-core, so you can let one processor work for the media player, you can let another processor work for the word processor, or maybe if you have more than two cores, you can let the third processor work for something else. So that is the architecture. So the multi-user is easy, but still, even though in the multi-user architecture, you still need to use the same memory, because there's only one memory that all those processors need to be using at the time of execution, right? If you remember our PEP9, you had the memory. After execution, you flush the memory. After the execution, you flush the memory. Your memory get clean. So for the new program, right? So you start from the scratch again. But in the real world example, it's not the same. Your processor is using, or the memory is being shared with multiple processors. So, and the third type of the program that the textbook talk about here is the real-time program. So those are kind of application that you will see, like say my example that I took previously was, assume a microwave or maybe smart refrigerator or maybe a washing machine with a tiny digital display, right? That can take certain instruction to perform a limited number of actions, right? So that is also a real-time operating system running behind it. I know that operating system is not as fancy as a Windows or Unix, but those very tiny operating system can run the functionality that required to make that device operated, right? So those are also operating system running in the background. So those are, we call the real-time operating systems. Everyone get the idea of different type of operating systems, right? So now with that being saying, so assume even in a PEP9 architecture, you want to run more than one application at a time, depend on which, excuse me, depend on which application that you need to send to, the processor. How the processor architecture being organized will be varied. So let me pull out how the memory architecture in PEP9, if you remember this right, as you see it here, from 000 location to FB8F. Everything in between this is being used for the application program. From FB8F to FFFF is being used for operating system related memory addresses. Operating system related memory addresses. So even though you see that this portion is larger, but if you carefully pay attention to the numbers, see 000 to F, right? That is almost 15 out of 16 of the memory size, right? So only F area is assigned for the operating system. Everything else is assigned for the applications. So that means the larger portion of your memory is allocated for the applications. Comparatively, 1 out of 16 of the memory is allocated for system or the operating system programs. So as you see it here, you have the global variables assigned in the application program and the heap and the runtime stack. If you remember, the FB8F is the runtime stack, initial stack pointer. Then depend on the size of the stack, you keep it incremented, right? Remember when you jump into the runtime stack, you increase the stack pointer by sub number of pointers that you need to bring it up. So this is that area. Then similar stack is being used with the system. System also need a similar stack. That's set to be start from FC0F towards FB8F, starting from FC0F up to FB8F. So that area is being reserved for system stacks. And any system global variables, and I'm sure that you familiar with these two numbers, FC15 and FC16, which is input device location and the output device location. And after that, you have areas reserved for the loader and one called trap handler. And also a few other 6 instructions that you see here, FFF4, 6, 8, A, C, E. Few last instruction also reserved for something. So that is because when you're dealing with multiple programs, we call it operating system will load your application to a state before it's get executed in the processor. Then as soon as it get the permission to be sent it to the processor, so you will send it to the processor until you fall into a trap. So one another thing that before I move into this trap instruction. So this trap instruction are a little too detailed, but I'm sure that you can read and understand. Even though it is expected to be known in detail, I'm not going to question you on this PEP9 program code for this particular chapter. Okay, do not worry about memorizing any content for the chapter 8 for the PEP9, but all I want you to do is get the idea of how the processors being handled by the process being handled by the processor in PEP9 architecture and in general in all operating systems. You get what I mean? I'm not expecting you to know all the PEP9 codes, because that will be a little too much for the rest of the semester. We only have few weeks, as the last few weeks in the middle. So my expectation is for you to get the idea of how operating systems handle the operations or process within its processor. So to have a better understanding of that, as you see it here, see the FB8F, which is the area that you perform your runtime stack, and some other instruction is kept here, and FC15 is the character in and character out. These are familiar instruction for you. These are familiar instruction for you. And there are some other instruction also used here. So again, so you have a loader area, you have a trap handler area. There are some specific instruction that you need to deal with when it come to handling the traps. Okay. So now, before we go into a trap, idea of being trapped, getting trapped in the time of the execution, how the program will execute more than one application that is running in single processor. Assume you have a single CPU. So how the program gonna execute it will be, you're gonna load it and you complete the job one. Until you complete the job one, you cannot go to the job two. So it's kind of you load everything that you need to get the program executed, then you get the program executed, then flush everything out, then you load the second program, right? And so do the same, you continue until you complete all your expected program. So now, if you do it in such a way, it's all fine. But unfortunately, it's not gonna be the same always, because sometimes you will see some program which is held by some other input-output interaction or some other resources, I would call it. So not all the program gonna execute smoothly from start to the end, regardless of user inputs, right? Some are expecting user to input certain values, right? Some are expecting your processor to generate certain output. Let's say if two programs trying to print a letter out using a printer. If two programs trying to do the same, so you have only one printer, it has to be always one after another, right? Both the program cannot send the print command at the same time. At least a milli or microsecond difference need to be there. Only one can be sent to the printer at a time. So to handle that, we call it kind of a trap, because why we call it a trap? Let's say if the one program is waiting till the other program, if one program is waiting until it gets certain instruction from the user, let's say you're trying to do a simple calculation, you enter one value, until you enter the second value, the program in kind of a hold state, right? It cannot perform. So while your program is in such a state, there is another instruction. Let's say you forget to insert the second value. If there is another program trying to do something different, like say it's gonna print out another value, if that value is already in the memory and if that second program can continue, so you basically put a first program into a hold and let the second program continue. That's the most ideal way, because you don't need to wait till the job one complete all the time. If in case you can complete the job two, regardless of what the execution pattern of the job one. If job one needs some certain input, you don't need to wait till the user enters such a value. You can just move forward for the job two. Everyone get that idea? Right? It's very simple, as you know, in a real world example. Actually, I took the same example throughout the last session. Let's say uh, if two of you trying to use a textbook to answer the homework assignment questions are written in the textbook. If one person waiting, if the student one using the textbook to answer the question, while he's answering that question, maybe another second student can answer let's say the third or fourth question without even having the textbook, because the question being given in the instruction sheet is itself, right? He don't need to depend on the textbook, right? So once he complete that question that don't need the dependency, don't need any instruction from the textbook, then he can go back and see when he want to answer the same question as the student one who need to access the textbook. Later he can go back and borrow that to answer the question. Does that make sense? How the programs need to be executed? So that's the requirement. So now to handle this, we do deal with certain different approaches in a program. So again, these are the trap related pep9 commands. I'm not expecting you to memorize any of those. I'm just gonna pass through those, but keep in your memory. If you want to handle traps, yes, those has to be handled using an assembly. Each one of those can be handled. But I'm gonna give you overview of how you're gonna deal with a trap and how you're gonna handle it and how we're gonna move forward from one process to another where you fall into a trap. Okay. That is the state diagram. Right. Okay. So now the question is, as we do have these trap handlers, even though we are not overly worried about how to write the trap handlers using the pep9 architecture, but we need to have a clear understanding how you're going to deal with when you have concurrent processes. So now for an example, now you see in the figure 8.7 that you see in my screen, there is one application in running, and that application is expecting a decimal input, right? Until the decimal input is being given to that application, your processor basically fall into a trap, right? Because if you're always trying to wait till the first application being completed, your processor will never move forward from here. So, but when your program get the decimal input, you can move forward and fall into the decimal output and complete the program. But what you can do is, as an alternative option, while the application is on running, while you are waiting for the decimal input, if user decided not to insert the decimal input at that point, you can get any other application continue while you get the decimal input, right? While you get the decimal input. But now the issue is, as you have multiple process running in a single CPU or single processor, we need to have a better differentiation between each one of those processes. So each one of the process need to be identified like this with a unique process ID. So process ID will identify which process is in execution at this point. So, and how much of a time that particular process will need to get completed from your CPU time. Basically, how many cycles in CPU need to be allocated for that process to get completed. So in order to do that, now you have your process ID for every process in place. If the one process is in the execution and if it's fall into a trap, you don't need to hold the entire processor. You can just let the next available process to proceed with its instructions until you get the required instruction for the process one. So we can draw a diagram like this to better represent that. We call this a state transition diagram. So your processor starting state here. As soon as you start the process, you basically as soon as you start your program, you create a process. That means you create a process ID, and we put it into a state called ready state. So process is started and put it into a ready state. That doesn't mean that it is executed. While it is in the ready state, if it has its all required resources to make things happen, if if you fall back to example like this, if it has the decimal input that need to move forward with this application, you move from ready state to the running state. If you have all required resources to continue, you move from the ready state to the running state. That means the processor in use for that particular process. So while you are in the running state, sometimes again you might need some extra information. Then it will again send back to the ready state. We call it, go through the waiting stage and to the ready stage. Now again, you are expecting more input or more resources to move forward. So this is how the processes being handled using a single process. Process being handled using a single processor in a real world scenario, because you only have a one processor, you have multiple processes coming towards you. Whatever process is ready to be executed, you send it to the processor. If you can continue, you do that. If you need some resources, you send it back to the ready stage again, keep it in the ready state. Once you once you are done with all required resources, you go back to the running stage and complete it. And once you're done, you basically finish the application and raise the flag differently. Everyone get that idea? The state transition diagram, how the process being executed in multi-process environment with single processor.
Seems to make sense, yeah.
Okay, good. So now, assume if you expand this little bit further with multiple CPUs with a single memory, because this is what we experience in a modern day computer environment. You have a single disk most of the time with multi CPUs with single memory. So now if I go back to the same example, you have a Word application running here, the media player application running here. Word application use a single CPU, media player application use another CPU, but you still have the same main memory. So you have the same main memory, but these memories are quite large. It easily can accommodate more than one process at a time. So each process will take its own data from the main memory and communicate with the disk sometimes if it is required, because some of those media files is permanently saved in the disk. You need to take those. So remember, if you remember the system bus that I explained in the first couple of weeks in the Newman one Newman architecture. So you take data through the system bus to each one of those CPUs. One another additional information about the computer hardware, if you remember it right, I said to you all, if you don't match the speed of the system bus with your memory, that's never gonna be useful, right? If you install a brand new system memory with like a high speed, but if your if your main board system bus speed is lower than the memory speed, it's never gonna be used in full effect, even though you have a high speed memory. Okay. All right. So now with that being said, if in an ideal world, in an ideal scenario, the best possible way to get the processors being executed will be the one straight line like this. So whenever one processor is in hold or wait, the next processor will come into the play and it's continued. And as soon as that processor is continued, if you have a third process, that's also come to the processor and continue. Whenever the first process do have its all required resources, it can fall back to a stage where into the running state and continue. So if that's so, the processor will be always in use. Your curve, there won't be any curve. You will experience one straight line. But that's not the real world experience that we will see. Even though that would be the ideal scenario, I'm sure you always experience your computer get frozen, right? Sometimes your computer get frozen because multiple applications are running. Only way to get out of it would be, you can, if it is a Windows machine, you will hit Control Alt Delete and go to a task list and kill some of the tasks that not responding, right? So that means even though we expected one smooth straight line, it's not going to be the same, but it will curve it a little bit down. So the performance rate is little lower than expected. If I take another example, if I take another example, like in a, so even though this is what we expected in a Mac OS, you will do the same. If you remember, in Mac OS, you will have this force quit option, right? You hit the force quit option that will list down all running application. From there, you can terminate any not responding application to free up your memory. So keep that in mind. So in ideal world, we all would love to have our processors being used all the time as far as our process need processor, but that's not what we experience. It will always give a lower results than the ideal results. So how are we going to handle such a scenario? So in a programming language, what we do is, let's say if we have two concurrent processes running, process 1 and process 2, what we would do is, as we have a two processor IDs created in the previous figure right here in the 8.18. So process ID is being created. As far as we know which process is in use, we accommodate accordingly. To better explain that, I will pull out this example here. So we call identifying a critical session. So if you have two processors, that's going to share some critical information. Let's say if you have a global variable declared, if both of those processors going to use that uh, critical information. So if one process is in use of that particular global variable, the second process should not grant any permission to access that variable. Why? If you give it if you grant such a permission, the variable will be modified instantly twice. You will see some results that not you are expecting. The real world example for this would be, assume you have a mobile application for your bank, and you are right in front of the ATM, and you have $1,000 in your account, and you are trying to withdraw $900 from your mobile, sorry, you are from your ATM, and at the same time you are trying to um, transfer another $900 from your mobile app. I know it's not really possible for you to hit both ATM withdrawal button and your mobile transfer button at the same time. Even if you hit it, there'll be at least like a microsecond delay that's gonna perform only one, right? So this is a real world example of you handling this as a critical section. So what it mean by that? So to handle this, what we do is, before we enter into a critical session, we basically create a kind of a flag. While a program is in its critical session, you will not let the same program or the same variable being used by another process. Does that make sense? So while you're completing your action at the ATM, at the time that you're trying to withdraw, your mobile application transfer will be hold for a while. That's what you see here. You enter into a session, then if you are into a critical session, logging into a bank application is fine, because logging in doesn't make any changes to your application, right? Logging into an ATM by entering the PIN code doesn't gonna change anything. But if you are trying to perform a transaction, then that's the time that your variables your variables are going to be changed. At that point, while you are in a critical session, and until you execute the session and complete the remainder session, you keep while equal not done. While this is not done, your second process will not execute. Does that make sense? Right? While the first process is being executed, your second process is not executed. We
I've
call this first attempt at mutual execution. Let's see here. So you have a variable called uh, variable turn, while the turn is not equivalent to 1, the process 2 have while the turn is not equivalent to 2. When you are in the critical session, turn is set to be 2. Turn is set to be 2. That means if the turn is not set to be 2, this is never going to happen, right? Because this is only going to happen if it is not equivalent to 2. Process 2 is never going to happen while the turn is in 2. So at the point that first process fall into the critical session, at the time the first process ATM trying to take the money out, the banking application is kind of in a hold. It cannot perform a transaction. After you complete it, then when you fall back to the remainder session, when it is said to be done, then that is okay. Then you can go back and complete the uh, uh, process two, right?
So I have a
Yeah.
question.
Yes, go ahead.
So if let's say the initial one process is using that variable,
Mhm.
you can still access and view it. You just can't manipulate it in any
That's
way.
right. That's right.
Okay.
Because it's like you are logging into a mobile application, and at the same time you can log in into a ATM machine using your bank card, right?
Right.
Right. So that's okay. That's perfectly okay. If you, let's say, in the different way, as you cannot go to ATM machine right now because of the restrictions, you probably don't want to use a ATM machine. So
Yeah.
you can log in into your a banking application using your desktop and your mobile, right?
Mm-hmm.
That is completely all right. But at the time you're trying to do a transaction, right? At that very moment, you fall into the critical session. Then you are setting turn into 2. That means whatever the other location that you logged in, it's said to be false. It not
Mm-hmm.
let you perform the similar transaction in the other session. So that's why this banking application. So you have to be well aware of the session and the time of the transaction, right?
Mm-hmm.
Otherwise, people can easily manipulate this application to do a, like, having $1,000, you transfer it twice, right? So you have 1,800, even though you have 1,000 in your account, right?
Quick question though.
Yes.
So this is looking at like one system with multi-processors. Like,
One process with multi-processors. Sorry, one processor with multi-process. Yes.
oh, we're still looking at single processor?
Single processor. Yes.
Oh, okay. Okay.
So see, more process, but single processor.
I see. Okay.
So if you have at least 2 processors, you can let the 2 processors work, right?
Mm-hmm.
Then you have to think about the third process that's going to interrupt the system,
Mm-hmm.
right? So it doesn't matter how many process really you have, you will have like a plenty of a process running on the same machine. So you always experience this. So second attempt to the mutual exclusion. Now here, what we do, this one is you have a variable set to true. So before you enter into a while loop, it is being set to be true. While you are in the critical session, it is set to be false. It's very much similar to the previous one. You have a value that's set to be 1 or 2 to decide whether it is in the critical session. Now you have a variable boolean value set to be true and set to be false. The enter 1 is set to be false while you are in the critical session. This also going to do the same thing, right? Once you complete the critical session, your remaining session will be executed and the while loop is done. While you set it to false, this can be executed, right? So there's another way that you can continue with the 2 processes by keeping a flag, So basically, if first one is true, the second one has to be second one is false, and the second one is true, uh, and the both are true. There cannot be a situation that you can continue with both the entries if the both are true. Only when one is true that you proceed with the processor. Da, 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 da. And you can of course have a combination of that. It's not always two process that you will experience. You will have multiple of those. So you can always work with multiple of those if you need to deal with more than one processes. So the same thing is being implemented here. Then okay, now with this approach, your state transition diagram is a little bit modified here. So you have your start stage or the state, then you have your ready state, So then you go into the running state. Once you are in the running state, you may have some input that need to be included to complete the application. Then you fall back to the ready state one more time. So what we do is one additional thing, you can put it into a waiting state with a variable s, and also you can raise a signal s as you for sending it back to the ready state. So there are multiple ways how you handle this. So you can have a wait state. We call it mutual exclusion between two variables. So you have an additional state as created. If you are in the waiting state, waiting for some extra information, you are not going into a critical section until your signal is set to be raised. Once you get the certain signal from your process, your application, then you fall into a running state, right? So there are, it's like a, I don't know, it's like I can explain it in a way like, if you are looking at a station where the train stops, you know, when you are given a certain light signal, your train will move, right? Even though there's no train in front of you, if you are given a stop signal, you will stop, right? So same way, if when you're driving, even though you don't see any cars in front of you, when you are in a junction, you are given a red, you will stop regardless of what in front of you. So that is to making it sure that you have all the information to move forward. Once you have that, and when you are given the signal, you move forward. So you are in the car, you know that your road is empty, but you not go forward until you get the signal. Okay.
Sorry,
Yeah.
I just have a question about that diagram.
Mm-hmm.
I understand everything except for just the timeout piece. What's that where it doesn't go to waiting, it goes back from running to ready? What is that like? Yeah.
So this is the thing. So when you are in the processor, when you are sent to the processor, you will wait for certain amount of time until you get us input. If you don't get the input, you will fall back to into a ready state.
I see.
That it's like, you know, some banking application will automatically sign off
Yep.
if it doesn't get a response, right?
Mm-hmm.
Right, even though application is up and running, it will sign you off automatically
Yeah,
because
that makes sense.
yeah, a certain time is been out. Okay, now for the deadlocks. So the next last session of this chapter is talking about the deadlocks. Deadlocks are where the situation, even though we would love to have all possible scenarios handled to make it sure that smooth completion of all the processes, that's not what you experience. As I said a little while ago, your computer may get frozen, right? Even after the years of research, even our Windows machine, Windows operating system gets stuck. Our Mac OS gets stuck. Your mobile devices get stuck, right? So that is because even with all these background knowledge, still there can be situations, sometimes the processors fall into a deadlock that cannot move forward. So by design, the architecture of building operating system is to guarantee or minimize the scenarios that your operating system that can be fall into a deadlock. If you can, I know that it is not possible to guarantee a 100% satisfaction. At least if you can keep it to a 90 or 80%, that is a satisfaction, right? Not always that you can guarantee that you will not have a deadlock, but if you can guarantee it to a certain level, that's what we need. So to better explain, I have some other web resource that I pull out, because this easily explain the 4 scenarios that you need to avoid a deadlock. So as you see it here, in order to avoid deadlocks, we need to making it sure that our processor and process do not fall into any one of those traps. So the first one is called the mutual exclusion. It says there should be a resource that can only be held by a one process at a time. In the diagram below, there is a single instance of resource 1 and it is held by process 1. So if you have a single resource and if you have a one process, that's good. That's good. You will never fall into a trap where, you know, multiple processes, multiple process you looking for the same resource, multiple process looking in for a same resource. If your process is always looking for a single resource, you're good. you will not experience a deadlock. That's what we call a mutual exclusion. Every resource that you use in your process, your program, is allocated for only one process. But in a real world, this is not possible, right? You have a single printer that can be used using almost all your application, right? You cannot have a one printer for every application you use. So you have a single resource. Therefore, we need to think about certain other considerations. So now in the second example, we call it hold and wait. You have a process 2 that's holding resource 2 and 3, but it's also in need of resource 1. But unfortunately, resource 1 is already allocated to process 1. So therefore, process 2 cannot complete until process 1 is completed. Good thing is process 1 is not depending on any other process that hold by process 2. Therefore, once process 1 complete the its execution, resource 1 will be released. Then process 2 is eligible to take it because it is already keeping a one hand on resource 1. You get that? Right? So if your environment is look like this, you still avoid deadlocks. Yes, you are in a hold, but after a certain time, you will still continue. It's not a deadlock. And the other option is we call is a non-preemption, preemption, which is a resource cannot be preempted from a process by force. So no process can take any random resources by force. No process basically has a higher priority than anything else. Of course, there are some prioritized process, but in general, you can say the all processes has equal priority unless otherwise it is given a additional priority. Therefore, each process will have some resources allocated. So as you see it here, process 1 resource 1 is allocated to process 1, resource 2 allocated to process 2. Now resource 1 is requested by process 2, but process 2 never gonna complete until process 1 is completed. Once it is completed, yes, it can continue. So if your situation is like this, still you will avoid any deadlocks. And the last but not least, this is one another important way that you need to avoid: circular wait. So if you experience something like this in your process architecture, your program basically fall into a deadlock. Why it is? See, as you see it here, the process 1, resource 2 is allocated to process 1, and process 1 also in need of resource 1. And the resource 1 is allocated to process 2, and process 2 also in need of resource 2. Now, this is like you have a one textbook and you have a one online exam, two students trying to take the same exam with the textbook and the one computer, right? And one is holding the textbook and the other one is holding the computer. One is holding the computer saying, okay, if you give me the textbook, I will complete it first, then you will take it next. But the other guy is saying, no, you give me the computer, I'll complete it first, and then you can take it second, right? So both are arguing with each other, but none of them gonna release their resources. So therefore, there will be a deadlock. So if you're gonna build a operating system that better manage its process, so you need to avoid this circular wait. If you're waiting in a circular way, one holding another and the other one holding another, it can be more than 2. It can be 3 processes holding each other. This never gonna end. So the only option will be you do Control-Alt-Delete and hit kill task. Okay. So you get the idea for the 4 scenarios that you need to avoid in order to making it sure that there's no deadlocks happen in your operating system.
Could you like put this on Canvas?
This
That
link, yes,
just,
I can.
I mean,
show it.
I guess it's in the recording too, but that link would be nice to have on my.
This link can explain it better. I can do that, sure.
Thank you.
I will do that. So because the textbook explanation is somewhat fuzzy, but it's not bad, but this make things a little easy. So that's the overall idea of this chapter. So again, I'm not expecting you to write any one of these trap and handle commands, but keep in mind, so those can be implemented using assembly. But all I need from your end would be for this chapter, how the process being handled when you have a single core and when you have a multi-core. So process will be sent it to a ready stage and to a running stage. If it is in the running stage, that means it is executing in your processor, but not always it is possible. If you are waiting for some additional information, you have to fall back to the ready stage and take some more inputs and move forward to the running stage. All right, so that's all I planned for. Any questions? I'm on time, you know, perfect. 1 minute before. I'm very accurate. Even in the previous session, it was 1 minute before I finished. Any other questions? No, actually, no questions. Tyrus asked few, that's good. All right, if you have no other questions, let me stop the recording. Oh, yeah, post